1 or 2 more sentences from the person standing here.
Hello. So this is Mike Bayer, and this is his talk, Hand-Coded Applications with SQLAlchemy. This is a 45-minute talk, so please don't exit until the questions end at the end of the session. Thank you.
Hi. Thanks for coming. So pretty exciting. I'm going to talk about some SQLAlchemy philosophy, and actually those of you who saw Brandon Rhodes talk just earlier, kind of similar concept, although coming from a maybe different perspective. I really appreciated Brandon's take on how disk access works. That was really fantastic. So we're going to start really basic here. What's a database? So a database, as we probably know, we can put data in and get it back out. And when we store data, it's sort of some kind of record or a row or a document. That's kind of what databases are doing for us. Within a record or row, we're going to have sets of attributes. Nothing mysterious there. And we're going to do queries that allow us to find records that have specific kinds of attributes. So that applies to pretty much any database that I've ever seen. Relational database, make it more specific, the fundamental storage unit in a relational database is the column, which is composed into rows. Those are then composed into tables. When we do queries, we can take rows from multiple tables and transform them into new rows composed from multiple tables together using joins. So that's kind of a degree of flexibility that relational databases give us. We can also make something called a derived table, which is kind of like a subquery. It means that we're going to take some rows within our query, and that becomes something that we can then further select from, which I find pretty cool. Relational databases give us lots of cool stuff like set operations and aggregate functions and groupings, recursive queries and triggers and functions and stored procedures and all that stuff that we associate with relational databases. And then the entire thing happens within the realm of transactional guarantees, which we know is the ACID model, atomicity, consistency, isolation, durability. And we're going to talk a little bit later about the C in ACID, which I find to be fairly important. How do we talk to relational databases? So we know in Python we have the Python database API, which is kind of typically the lowest level that we use in Python. DB APIs usually talk either to the network protocol or to a C API for that database. Then we have abstraction layers, which is anything on top of a database API, and to some degree within some DB APIs. And then on top of that, you have object relational mappers, which we're going to talk about mostly. And here's kind of a view of that. To the left, we have the lowest level of abstraction, and to the right, we have more abstraction. And DB APIs are kind of start to become abstraction layers, and ORMs maybe start to become more than an abstraction layer. That's kind of just a way of looking at it. So what's an ORM? The first thing we do with ORMs, the most obvious thing, is that it automates the persistence of our domain models, which are like our object-oriented class hierarchies, into a relational database schema. So we all know that. It provides the ability to query and compose SQL statements in terms of our object model, our domain model. And then when we get results from a database, it retranslates those relational results back into instances of our class's domain model state. So, okay, that's basically the round-trip model. And then something that ORMs do to differing degrees is that it can mediate between object-oriented and relational geometries. So a relationship is kind of if you have two classes that have some linkage to each other, like a collection, an ORM will relate that to 2 tables or 3 tables with foreign keys between them. Some ORMs can also do inheritance, like if you have a class inheritance hierarchy, it can represent that in a relational database as maybe 1 table with a discriminator or several tables. So those are things that object-oriented, that ORMs can do for us. So how much abstraction should an ORM provide? And we're talking here about abstraction as hiding first. So would it conceal details of how the data is stored and how it's queried? Would it conceal that the database itself is even relational? Which means, would the same interface be used to talk to MongoDB? Would we get non-relational data back from the same query interface as we do a relational store? And these are questions that are asking to what degree we should be hiding things. So there's another way of looking at it. Well, first we'll say what are the problems that we might have if we consider ORM abstraction as to what degree it hides the database. Well, as we just went over, the SQL language is relational. It has a lot of great things that we like, called like joins and unions and derived tables and all that other good stuff. And the ability to use those things and to refer to them, and as Brandon said, to ask just one question of the database, that was really terrific, is kind of the primary feature of relational databases. We really want to get at that stuff. If we're using an ORM that is hiding it, it means you don't have first-class access to those features, which means the ORM might be using some of those features behind the scenes, but it's assuming that we don't want to deal with it ourselves. It's going to do it for us. It's going to kind of guess. So that's why we have kind of second-class access with some approaches. So in that scenario, the relational database is underused or misused, and I think this is where we get the term the object relational impedance mismatch from. When you read articles like that, they're talking about ORMs that are trying to make too many decisions for us. So we don't really want to hide things. What we want the ORM to do for us is automate the work of dealing with the database. So we're best off when we design and control the schema and query side, as well as how our object model interacts with it. And we still need tools to automate this process. So I'm going to, within the scope of this talk, I'm going to say the concept of explicit decisions plus automation via tools is quote unquote hand-coded, kind of a buzzword. So SQLAlchemy and the hand-coded approach, now we're going to go into what that is. So hand-coded, what does that mean? And here's a little Twitter stream from Doug Hellman where he was like, well, what does that mean? How else did you make an application other than by hand? So, I Googled around to find some of the tools that some of us might have used when we used to work at banks and stuff. This is an application called Oracle Application Express, which is where you get a wizard interface to something. You get like these pie charts, so you can kind of select what you want. You open up your Excel spreadsheet, and you cut and paste some data. It's basically just the wizard's going to do it for us. You push a button, and this is Formus Creare from a mythical Harry Potter. So it's just magic. It's a wizard. He just did his thing, and then it's web scale. So these are slides from an Oracle. Now, actually, Oracle Application Express is probably not a bad idea because it's designed for executives who would otherwise be emailing spreadsheets to each other. So it's not terrible, but they're a little disingenuous when they say that you're building your own web app, because it's not really quite the same thing. So, Zeke, that's a silly example because that's really not at all what we do in Python. None of us use tools like that. But that's an extreme. When we use tools that make schema design decisions for us, they conceal the database in relational geometry and give us a pass on having to obey ACID, some of the letters within the acronym there. I consider it to be kind of a step in that direction. We give up some control of architecture of our application to a third party. So the hand-coded approach means that we're going to make the decisions about everything. We're going to implement and automate those decisions with tools, and we're going to retain control over the architecture of things. Hand-coded is the opposite of apps written by wizards. That's obvious. It's kind of the opposite of apps that rely very heavily on plugins, meaning the way you write a program is you go and get 6 different plugins and string them all together, and then you put them into a package, and there's your app. That's kind of not really hand-coded. You're kind of letting third parties design what you're doing, which is not a bad thing, but you should just know that that's what you're doing. It's not the only approach you could be taking. And then using APIs that make implementation decisions, which is more subtle, and that falls into the realm of trade-offs. Sometimes we do have to use APIs that make implementation decisions. Sometimes we should say, this API is really not worth it for what it's going to do to us. So hand-coded doesn't mean that we don't use libraries. We use those as much as possible. It doesn't mean we don't use frameworks, because they're great if they don't make things harder. And it doesn't mean that we don't use defaults, although what I'm going to show here is in SQLAlchemy, we kind of define our own defaults as far as how schemas are designed using self-established conventions. I'll show an example of that in a minute. So what are some examples of implementation decisions made by APIs and hiding? So the first example I'll show is the polymorphic association pattern, which is something that I first saw Rails doing. I think a lot of PHP ORMs do it, and Django also does it. And the next, if I can get through it all, will be querying approaches that oversimplify relational geometry. So for polymorphic association, and actually for the second example, we're going to start with this kind of myth. This is not SQLAlchemy. This is just any old object relational tool. We're going to do a financial application where we have an entity representing a bank account. So if you have a checking account and a savings account, you'd have 2 bank account records. And a portfolio asset, which is like you own 100 shares of Apple, you'd have a portfolio asset. If you own some shares of Google, that'd be another portfolio asset. So that's kind of two entities we're going to start with, and they have, a string name of the person who owns it, which is probably not how we would do this in real life, but just for the sake of example. And they also have a symbol to identify which stock you own, and an identifier, which is your bank account number. So now we want to use some mythical library called Magic Library to add a collection to each of those objects to an object called the financial transaction. So this is what the polymorphic association pattern is usually giving us. It's the ability to take a single class and associate it with more than one kind of parent. What financial transaction will do here, it's going to store how much money we have in these accounts and assets using an accounting model where you store the amount of money based on individual credits and debits. So if I have 3 financial transactions, one for $50, one for $100, and one for -25, I'd have $125 in my account if I did the math right in front of all these people. So that's what that looks like. So usage, you have a bank account, you add some transactions to it, it's got a timestamp and an amount and portfolio asset transit. So that's what that looks like. And then the generic reference, behind the scenes, without us really telling it to, did this thing for us. It did all the work for us. It created a schema like this. And this actually is pretty close to what Django's doing, and Rails does a similar thing. We have our bank account and portfolio asset tables, and they then contain a collection of financial transactions which are rolled up into one table, which is not necessarily a bad thing. There's ways to do that. For each row in financial transaction, we have this column called content type ID, which represents a discriminator. So for each row, the content type ID will refer to one row or another in the other table over there called magic content type, which will tell us for each row in financial transaction if we're in the portfolio asset table or if we're in the bank account table. So that's a discriminator, which is not necessarily a bad thing. The discriminator for the magic library is actually storing the module name and the class name of the bank account or portfolio asset class, because that's how it felt like doing things, which, is one way to do it. And then for financial transaction has another column called object ID, which is an integer that might be an entry within portfolio asset, or it might be an entry within bank account. And we don't know which one it points to unless we look at the discriminator. And so in relational databases, we have this concept of a foreign key, which is an integer column that refers to the primary key of another table. And the database will constrain the values within the foreign key to be only those of the primary keys that are available. And that's part of how the relational database maintains consistency, which is the C in ACID. When you do this pattern, they sometimes call this a generic foreign key. The database is not able to constrain object ID. You could actually have rows in financial transactions that don't point to anything, which means if you're going to do a report of how much money we have in our company, you could get the wrong answer. You could get, in my view, it's a corrupted database. So it's actually up to, and the usage of the model would look like this. So magic content type gets these 2 rows, one for bank account, one for portfolio asset. Financial transaction gets these rows where the object ID points to one or the other, and that's what it looks like. That's what Magic Library is doing for us. So the implicit design decisions here, as I started to talk about anyway, it added this magic table to our schema, which, that's fine. We don't care. It's adding a table. It might not conform to the conventions that our DBAs want us to use. It's just kind of this extra table. The magic table is storing Python source code within it. It's storing the actual module and class name in there, which means if we want to change our application structure, we have to change the data. Magic Library gives us some command called update the database, which takes care of it, but still, it seems like why do we really need to have that going on? The storage of transaction records are on one monolithic table, which might be what we want, but it's a decision that was made for us. We might want the bank account rows to be in a separate table than the portfolio assets. If the portfolio assets table had millions of records and the bank account table had thousands, we're using PostgreSQL. It could make very different decisions about optimization based on if we're joining to the bank accounts or the portfolio assets. So it's not, you can use one table, that's fine also, but the point is that the Magic Library didn't give us a choice and didn't even ask us. And then the biggest concern is the schema design here is not constrainable. So the application layer here is responsible for maintaining consistency and not the database. So SQLAlchemy's approach, on the other hand, is to encourage us to specify how tables are designed and mapped to classes explicitly. We're going to use regular Python programming techniques to establish composable patterns. And this approach will express our exact design fully, and as I'll illustrate, if we do it correctly, can eliminate boilerplate at the same time. So this is a typical SQLAlchemy model. If you look at our tutorial, we have you define a class, and the class has to pretty much specify everything about the table that we need to know. It doesn't make any assumptions about the names of tables. It doesn't make assumptions about constraints or primary keys. We have to tell it that these two classes have a primary key called ID, which is an integer. It makes no assumptions. So let's try to see if we can kind of trim this down and remove some of the redundancy. What you can do with SQLAlchemy declarative is you make this class called the base, which is where your classes all extend from. You can customize how the base works. You can make what we're doing here is a base that our declarative base will derive from. And we're using a decorator called declared atcher, which is from the declarative extension. It allows us to define a class-level method on a class that will act as one of the declared attributes, such as table name. So with this is establishing a convention for all of our classes that they will have by default. This is where we are making our own defaults, a table name that's derived from the name of the class, basically converting from a camel case to words with underscores here using a regular expression. And this only happens at module startup time. This isn't evaluated. This is just when you first run your app, those table names will be evaluated, and that's the only time it happens. And then we're going to give all of our mapped objects a single primary key column called ID, which is an integer. So then we make the declarative base, and so we won't have to do that anymore. And then we'll also make some patterns for classes having an owner, like someone owns this account. We'll start out with a string column, and we can later change this has owner mix in to refer to another table. And we'll also remove the boilerplate of having to create columns that are unique and not nullable for like your bank account ID. So with those conventions that we just create once, we've put them in a util somewhere in our application, and we never look at them again if we don't have to. We can now make that same model we saw before with just 4 lines of code. So what we're doing here is we've made our own defaults. The ORM didn't give us defaults, but that didn't mean we had to type out the table name every time. We made our own defaults, and we did that. So continuing on that pattern, we'll build the polymorphic association using a convention called has transaction. So where that will begin is we're going to make a class that will represent how we store the transactions. And also maybe transaction was a poor choice here. It's a financial transaction, not a database transaction. So it has an amount of money and a timestamp. So this is actually not a mapped object. This is going to be kind of a template for future classes that will be mapped to tables. And then the one part that's going to be a little more dense here is this slide here. This is the most dense code. Well, later we'll have some more, but this one, this actually defines the polymorphic association. And this is the whole thing. So, you know, using the magic library is fine, but really, and this is just the only thing you really have to do to create the same functionality that the magic library did for us, or similar functionality. We're defining a mixin called has transactions. It has a declared attribute called transactions, which is going to return for us a relationship to a new mapped class called transaction. And transaction is a class that we've created anonymously using Python's type function. So we have type, and then we have, we give it a name, and then we give it a table name based on our convention. And then we give it a parent ID, which is a foreign key back to the parent object. So then we apply that has transactions to the model, and then we get bank account and portfolio asset. Okay, rudimental usage is similar, and the schema looks like this, where we're going to have just bank account and portfolio asset, and we just have these two tables, bank account transaction and portfolio asset transaction. We're no longer doing the discriminator table. We have kind of a cleaner design here. So a summary is we've composed has transactions using a well-understood recipe. We've used our preferred naming and structural conventions. We're using constraints and traditional normalized design properly. And the data is in separate tables per parent, and other schemes are possible as well. And the data is not hard-coded to the application structure or source code. So why don't we improve the generic reference system, the magic library, to support these practices? Well, generic reference would need to present various modes of behavior in the form of various options and flags. It might lead to a more complicated configurational story. And I would say that the polymorphic association is actually not that hard to do by ourselves. We can just, I consider it to be kind of a trivial pattern. It's kind of self-documenting, and it's actually easier just to have polymorphic association on our own instead of kind of bringing in a third-party library that might have a complicated configurational story. So that's the polymorphic association, and that's kind of the SQLAlchemy's take on that kind of thing. And then the second example is exposing relational geometry. So what we're going to talk about here is how we do queries with the ORM. So take a mythological, it's not really a word, take some hypothetical ORM and say we have some bank account and we want to get the balance of an account as of a certain date. So we might say, hey, some bank account, give me your transactions collection, give me the sum of the amounts, and the sum of the amounts will give us the balance for an account, and then we're going to filter those amounts to be those that are less than some particular date. And that will give us the balance of an account as of a certain date, and the obvious SQL is below, select from bank account transactions, and filter on those two criteria. And that's pretty simple. So any ORM, the hide the SQL system easily applied an aggregate field to a single field on a related collection with a simple filter. It's not very mysterious. So then what SQLAlchemy will say, well, in the real world, you probably will have more complicated queries than that don't map to the hide the SQL system so well, and we're really going to want to get at relational geometry explicitly. So suppose I want a report of the average balance per month across all accounts. So with that one, because our model is storing the financial transactions as individual amounts, we need some way to roll them up into balances. And we need a way to roll them up into balances such that we can really distinguish among temporal data. We need to group them into balance per month, basically. So we probably need to use subqueries or window functions to produce the balances as a sum of amounts. This is assuming we're trying to ask the database just one question, as Brandon said. In SQL, we would build a query like this incrementally. We'd make smaller parts of it first that represent a more general concept of data, like a larger span of data, but simpler, and then we can kind of join them together to get more specifically the information that we're looking for. And if we can't do that, we have to bypass our tools doing this. This is where we would either write a SQL statement as a string and just spit it out, or we would not even bother asking the database one question. We would go and just load all the bank accounts in and just sum all the amounts by hand, which would work fine for about a month until a year later when your bank account table has grown to like 1 million rows and now it doesn't scale anymore. So, we really do want to try to do this on the database side. So, SQLAlchemy's query model will explicitly expose the geometry of the underlying relational structures that we've designed. And it's kind of like power steering for SQL. It doesn't teach you how to drive. You're going to steer the car, but it'll just kind of help you with that. The developer should be aware of the SQL being emitted. We have the echo flag, which will show you everything that's happening. One of SQLAlchemy's main focuses is being very, very transparent about what it's doing. It's just like your car has windows to see where you're going. So we'll do this query in SQL first, and I'm going to show off what a window function looks like in a second. So we're going to start with a query that's going to extract all of the start and end dates of each month in the bank account transaction table. So we're going to go through all the financial transactions in the bank account transaction table. We're going to extract the year and the month from each timestamp, and then we're going to make groups. We're going to group on the month, so we're going to have these groups of rows within these month buckets. And then within each per month bucket, we're going to get the lowest and the highest timestamp within that bucket, so that we can just extract from the database where the months start and end relative to our data. Now, if we could also do a query that just gave us the first date and the end date of every month, that would work as well. But that would mean we'd have to use some kind of calendar arithmetic to know that February 29th versus 28th and March 1st through March 31st. This way, we just use the data that's already there to give us the ranges of timestamps that we actually would care about, which are the ones that are actually there. So this is one half of a two-part puzzle. The data we get from that query looks like this. So in March of 2009, the first transaction that month was on March 8th, and the last one was on March 28th. April 2009, we went from April 5th to April 30th, so that's what that looks like. So that's one half of the data we're going to work with. The other half of the data, we're going to use something that I've been using more lately called a window function. Now, a window function gives us this handy way to work with SQL aggregates, but in such a way that we don't have to group everything into one row and then just give you an aggregate for that group. It'll give you an aggregate for every row as it goes through the results. So we're going to get the idea of each bank account and the timestamp of each financial transaction and the amount of each financial transaction, and then we're going to sum them over the partitioning of the bank account ID and order in time. So I'm skipping, but what this means is that as we select rows, the database will first partition them into groups based on bank account ID. So each bank account ID will have its own list of financial transactions. They're going to be ordered by timestamp within each group, and then it's going to give us the sum of the amount within each of those groups, and it'll give us kind of a running total for each bank account. So this is what that data looks like. So for bank account ID number 1, those timestamps are individual debits or credits to that bank account, and those are the amounts, 7,925, 146, and then on the right we have the sum as a running total as it goes. And then you have bank account ID number 2 and 3. So what this query is giving us is every possible balance for every bank account that has ever been in the system. So it's every balance for every timestamp that the balance was unique. So now we have these two sets of data. We have ranges of all the months, and then we have all the balances that have ever existed. And then we can join them together, where I've created this novel color coding system to try to make it quicker to see what's happening, is that the blue parts of the query are from our ranges of months, and the red parts are from our collection of every possible bank account balance there ever was. And then we join them together at the bottom, where you can see the balance, the timestamp of each balance row is between the min and the max of the month ranges. So this is a pretty fancy query. And then we group by year and month in order to make it look better, and then we get data like that. So that's the average balance per month within our bank. Now that was kind of a weird query, but I don't think the example is too exotic, because it's pretty common that accounting data is stored as credits and debits, and it's pretty common that you're going to want to have reports of balances. So I don't think it's that crazy of a query. So with SQLAlchemy, we're going to build this query in a similar way. We're going to think in terms of simpler parts and compose them together. It provides the same inside-out paradigm as SQL itself. You think in terms of relations and joins the same way as when constructing plain SQL. Your brain's going to work the same way. And then SQLAlchemy, because we're staying within the ORM, we can do all the other cool stuff that the ORM gives us, like further generations upon that query, limiting, and if you had objects being loaded, you could either loading, all the good stuff that SQLAlchemy and other ORMs can do. But we can stay, so we're basically staying in the object model and in the relational space at the same time. Both are exposed simultaneously, which is really what SQLAlchemy, the choice that we made early on. So we'll make the same query, and if you know SQLAlchemy's syntax, this kind of lays out the same way. So we have first the month ranges subquery. So we have the min of the timestamp and the max of the timestamp, and we extract the year and the month, and we group by the year and the month. It's basically the same thing. And we have the all balances and timestamps window function. We've added window functions as of maybe 073, 074. It's just basically you say func sum of the amount, and then you say over, and you give it partition by what you want to partition by, and you order by what you want to order by, and then we make a subquery out of that. And then we have these two units, and then we compose them together. So select average balance per month is the query of the year, and the month of the month ranges subquery, and the average of the balance from the all balances and timestamps subquery. Select from the month ranges selectable, derived table. Join to the all balances and timestamps derived table, and then we're gonna do the join on the timestamp between the min and max of the month ranges. We can group by year and month, and we can order by year and month, and we get the same result. And then the SQL that it generates is more verbose, but I've applied the same color coding to it, so you could see that geometrically it's the same. It's got some more, SQLAlchemy is going to lay out each column with a label name. There's a lot of other things that help it in its job of relating rows back to objects. But it's basically the same thing. And the idea here is that we didn't have to change how our brain works when we moved from writing a straight query to working with SQLAlchemy. We did the exact same kind of thinking. So once you know SQLAlchemy's query syntax, you can really continue to think in terms of sets, which is really what you should be doing when you work with the relational database. So summary of good. And what's interesting here is that when I timed this talk, I was always right 45 minutes on the dot, and now I'm like way ahead, which is really weird, which means I probably went too fast. I'll do the whole talk again. It means I right in the middle, I was like, oh boy, I'm not explaining this well, and I just went right through it. So maybe we can go back if some people had questions about some of the stuff I obviously went through too fast. Summary of hand-coded. The developer is retaining control over the relational form of the target data. You're going to keep in control of what you're doing. I mean, it means that when you're given a problem to solve, and you're given the data that you're dealing with, you're going to actually design your schema. You're not going to piece together tools that are going to make the decisions for you. So schema design decisions are made by the developer. The tools are there to help you, but they should not make decisions. SQLAlchemy is then going to provide a rich and detailed vocabulary to express and automate these decisions. And then the developer will create patterns and conventions based on this vocabulary. That was where we did the thing where we had the has owner convention and the unique ID and the base class with a table name and an ID. And then the relational geometry remains an explicit concept complementing the object model, which means as we work with SQLAlchemy, it's not concealing anything except just some of the boilerplate of DB API and SQL rendering, but the geometry of relational algebra is always there for us in a very one-to-one way. Some people will say this is what you call leaky abstraction, meaning that you have this abstraction layer, but it's leaking, meaning there's concepts from the lower level being exposed. And this kind of speaks to the concept of abstraction, meaning hiding. This term refers to what I just said. So does SQLAlchemy's schema design paradigm and query object exhibit this behavior? For now, I would just say you bet, because it's not really totally concerning to me. I think the model we have works, which is that you're kind of doing the O and the R in ORM at the same time. And before, Brandon Rhodes also had this term called the O problem, which I just thought was awesome, and I'm going to totally take that on, the O problem, which is when you're only looking at the ORM in terms of O and not the R. So it's great. So if you want to call that leaky abstraction, I can't really help that part of it. I just have this quote from Joel on software that all non-trivial abstractions to some degree are leaky. But really the answer is I can't really care too much because I know that the approach works really well and a lot of other people like it. So it's leaky abstraction if you want to call it that. SQLAlchemy accepts this reality up front to create the best balance possible. And then we'll have a little bit of a graphical display, which is, suppose we had, this is Norm from the New Yankee Workshop. People know that show? It used to be on PBS. I used to like it because I used to like, this is before I was even doing Python, I just liked watching a guy who really knew what he was doing, and the things he didn't know he was going to learn. And he was really a master at his craft. So this is software as craftsmanship, right? And here he is building like a nightstand or an end table or something. And then the other side, and this is a little bit trolly, sorry, is designed by third party. I couldn't resist. Don't take this. It's just kind of a joke, haha. But it's like IKEA. It's like modular furniture and it's like mix and match. And it's actually fine. I've owned much IKEA furniture, but it's like if you really want to build something amazing, I would think you'd kind of want to do Norm's approach if you're trying to build something amazing. If you're just trying to build something quickly and get it out the door, fine. But if you build software with what I'm calling the hand-coded approach, you're building much more specifically what you want, accurately targeted and long-lasting designs that will resist technical debt. And technical debt means that you've made some trade-offs as your design, and you've accumulated them, and then a year later, you have this part of your app that doesn't scale because you really didn't write it in the way you wanted. You accepted trade-offs in the name of using third-party systems that kind of did things in not the best way that you would want yourself. So it's about being specific, but at the same time, providing a way that it's still not tedious. You still can automate. You still can have defaults. You just kind of have to design these conventions on your own and have them as part of your application. It's kind of part of application design. And that is the final slide. Yeah. Yeah. So what I can do is, because I went way too fast, I can go back to the slide that I went too fast on, the one with the polymorphic association. Would that be good, or do you want to have questions? Yeah. Go to that slide? All right. Because what happened on that slide was that I realized I was standing in front of a lot of people. And I was like, uh-oh. So let's go to that slide. So, and this is very slow. All right. If you download SQLAlchemy, we have a directory called examples where there's a lot of examples of things. And we have actually 3 examples of how to do polymorphic associations. There's 3 versions. One is table per subclass, one is one master table, and the third one I can't quite, it's some variant of that other one. I forgot exactly what it is. But what we're doing here is when you create a class that includes has transactions mixed in its class hierarchy, the declarative module will see this method called transactions, and it will call it, and then it's going to evaluate what's inside of it, and then the return result will be returned as though you had just said transactions equals relationship to some class. So what's happening here is when transaction is called, when you make a new class like portfolio asset, declarative evaluates that method, and then it will, what we're doing here is we're actually creating a new class on the fly. And the class on the fly is a subclass of the transaction base, which is this guy here, and also our declarative base, which is the base of all of our classes. And you can see that where it's calling type, it has a tuple of transaction base and base. Those are the base classes. So there's basically a class that is inheriting 2 other classes. And then we give the class a name, which is based, and also when this transactions method is called, the CLS, the class variable there, is actually going to be the parent class that we're building. So it would be the bank account class or the portfolio asset class. So that class comes in, it's called bank account. This will create a new class called bank account transaction. And then within the new class, you have this dictionary, which is the class dictionary. And it'll define for it a table name that's derived from the bank account table. And it'll give it a column that's a foreign key back to the parent. So this is basically, it's a little dense, but the idea is you just do this once for your certain patterns. And I actually do this all over the place for different kinds of patterns. You don't have to deal with this on a daily basis. This is just like a thing you do once up front for certain kinds of patterns you want to have. And then you just stick it away, and then it works. And everyone uses it. And if someone doesn't like what it's doing, or you want to change it, you just open up the source code. It's like 15 lines. I don't think it's that terrible. And you see what it's doing. It's transparent. And then at the bottom, we return a relationship with this new class. And we've also attached the class to the parent. So we have this thing called bank account dot transaction, which is the table that's the class that's mapped to that table. And in SQLAlchemy, in the examples, there's other variants of this. There's variants that will use one table for all the polymorphic associations, similar to what Rails does, but it has an extra table to add a foreign key constraint. So that's what that is. And I also have blog posts that show this, and there's a lot of background on this pattern. So that's a more advanced pattern. But the important takeaway is at least do things like this, where you have common patterns are defined up front, because it makes your code cleaner and more succinct and more specific to what you're doing. So that's that part. So I guess now we can do the questions.
If anybody has any questions, please step. That's the mic. Yeah, that mic is on.
So your hand-coded approach assumes you have control over the schema.
Yeah.
How does this apply when you don't?
Well, it doesn't. It probably is. That's a great question, which I didn't consider in this case. In that case, it might not apply as well because you're going to have to deal with the schema that you were given, and that's probably the flip side to the whole question. That SQLAlchemy is again exposing the schema and letting you do exactly what you want. So at least at the code level, you can do exactly what you want, and you don't have to worry about third-party libraries that don't know how to interact with that schema. For a long time in the beginning, there was kind of this meme that SQLAlchemy was for legacy schemas, which you can imagine I didn't like to hear that because I would try to say, well, it happens to work for legacy schemas, but it also works for the schema that you exactly want to design. So I would say, well, it works for legacy schemas, but it works also for your schema, which is the one you want to build. So the answer is, it would be a half hand-coded approach, where at least...
Well, the hand-coded approach I've used with some very extreme cases of 1,400 database tables with horrible composite keys across 10 columns is to build select statements, and that's the hand-coded approach there. Is to work with the select and the SQL expression APIs, which that's the only way I could have shipped is thanks to SQLAlchemy and SQL expression language.
Great.
So a follow-up question, and I'm sorry for you guys behind me, but this mix-in pattern is really great. And do you have access control examples with
like an example of a mix-in that does kind of like attribute protected access type of things?
That kind of thing.
I'm not sure if I have an example offhand. There might have been people that have asked about that. There might be some things I came up with on the mailing list to do that. It's Python. That's kind of how I see it. And with Python, you can use get attribute if you really want to put some central control. So yeah, I don't have a specific example because I don't tend to use that too much. But I mean, sometimes I'll use a custom validate. So if there's some attribute that I really want to make sure no one's doing the wrong thing, I'll put a validates decorator on it. That's in the doc. So it's kind of like there's not a simple answer. There's it depends on what you're doing. That is also hand coded. That there's no simple answer. Well, what's your actual use case? Who's up?
So how do you deal with schema changes when you have live data?
Well, it's just schema changes in general, right?
So I guess an example would be let's say for some reason I want to change, instead of the table being bank account transaction, I want it to be called bank account trans.
Then change the name of the table, you mean?
Sure.
Yeah. Well, okay. So, I mean, from the point of view of the code, you'd want to change your conventions, and then from the point of view of your database, you want to use a migrations tool. Early on, I didn't really get into migrations too much, but I use SQLAlchemy Migrate. Is your question about migrations basically, or you think more about code?
So it's I have hundreds of gigs of live data, and I want to, and it's a live product people are using all the time.
Yeah. Well, if your scheme is changing, we these days we use migrations tools. So there's a tool that I have called Alembic, which does schema migrations, and then there's also SQLAlchemy Migrate, which is the old school package, and it can detect. I think SQLAlchemy Migrate does this too, but Alembic does this as well. It can detect what you've changed in your model versus what the schema looks like, and it will generate for you a set of candidate upgrades, like, hey, I think you want to change your database to look like this. Is this what you want? And you get some code there, and then you basically run that script or correct it. Is that what you're asking? Or?
I think I'm asking more about what's the application code look like during the migration? So let's say that the migration takes a week to run.
Well, all right. So I think the model is you change your application. You're running in development first, so you change your application to the way you want it to look. So assume that the database has already been migrated, and then you create your migrations files that will do the database side of it, and then you run that side, and then that catches up to where your model is. So that means you don't have code that can talk to both schemas at the same time, and there's really no way to avoid that. Well, no, that's not totally true. If you're adding columns, then it's fine. Your old app can talk to your old code. I'm getting confused, but generally the code goes first, then the database is migrated second.
Maybe we can talk more later.
Okay.
Yeah, can you talk a little bit about maybe some cases where SQLAlchemy wouldn't fit as well, if such a thing exists, or maybe only the lower level
where you
parts?
wouldn't use SQLAlchemy? Mm-hmm. Well, obviously, if you're not using Relational, you wouldn't be using it. I think people that come to SQLAlchemy, I think from the point of view of learning, I think maybe you don't want to use abstraction layers when you first are learning relational databases. Maybe you want to just do it direct. Sometimes I've kind of toyed with this. If you're really doing a one-off, and I've written some one-offs, and I've said, hey, let me not use SQLAlchemy for this one-off, and I find myself reinventing half of SQLAlchemy anyway when that happens. You know, so I mean, I kind of designed it that you would be able, it has various levels of usage, so that it really is pretty flexible. So I don't think I have a great answer. I think if you find the ORM to be I mean, we have these two levels called the core and the ORM. The ORM is about mapping a domain model, and the core is just about a DSL for SQL. So if you're writing your application in a non-object-oriented fashion, you probably would just use the core. So you would use not the ORM part. So I would say that. Or if you're writing a custom persistence layer that is really not at all like the ORM's model, you might write a different kind of thing that uses just the core. Like Reddit built their website using just the core. So, you know, it's a question of degrees. It's not a black and white.
Hi. I wonder, can you explain when SQL Express is good for? I mean, in what scenario we should consider using?
The question is SQL expressions?
In what scenarios we should consider using SQL Express?
Say that again?
What is the use case for SQL expressions?
You mean using the core without the ORM?
Yeah.
Yeah, well, originally, the idea with SQLAlchemy was that the ORM dealt with mapping classes. There's some history here. Originally, the ORM dealt with mapping classes to tables, and then the querying was done mostly in terms of the core SQL expression. So that allowed us early on, when we didn't do much at the ORM level, to do everything that we could, because the core maps very closely to exactly how SQL looks. So originally the model was that you'd use the core expression language with the ORM, and then as the years went by, we kind of refined that so that the SQLAlchemy query object, which we didn't even have in the early versions, could in fact do most of what the core does. So if you're using the ORM, you probably don't need to use the core any more than to the degree that the ORM needs you to use it. Like when you use the ORM, you could say filter, and you can use the AND conjunction or the OR conjunction with ORM concepts. And that's the same OR and AND that you have from the core. So it's kind of this, the core kind of blurs into the ORM. So every question being asked, I have like this kind of loosey-goosey, blurry answer. You know, also, when you use the query, if you create a subquery out of a query, that's now a core select. So there's kind of just places where the ORM kind of naturally drops down to core. So it kind of is as the use case calls for. And if you're not using the ORM, then you use the core completely. So that's kind of the best answer I can come up with. Yeah.
Hi. So in cases where you've got the parent-child relationship, like you have with the transactions and the account, with other ORMs that I've experienced, when you do a query to get a bunch of the child, and then you reference the parent from the child, each parent is an individual object as opposed to having one object for that parent of all the children. They're like individual memory.
Multiple parents, right?
Well, so like one bank account, 10 transactions, you do a query and you get all the transactions, and you go from a transaction object to the parent. Yeah. If you reference each parent individually from the child, it's actually a separate object in memory?
No, okay, so it's the same object. SQLAlchemy, when you work within a session, which I didn't really describe too much here, uses this pattern called the identity map, which means that if you have a bank account with ID number 5, that object is given what's called an identity key, which consists of the bank account class and the number 5, and that's the only instance of bank account ID number 5 that can exist within that session. So if you load 10 financial transaction objects and you say .parent, it will, every time it loads any identity from the database, any row that comes in with an ID number 5 for the bank account table, it will go into the identity map and see if it's there first. So you get the same, and that's really key to the whole unit of work pattern.
That's cool.
Yeah.
Other ORMs didn't do that, and it's blown out memory.
Right. Well, we were
Yeah.
talking at the web summit I was talking to Jacob Kapamuscle a bit, and we kind of talked about possible SQLAlchemy Django somethings, but no, we don't know.
Thank you.
But he actually talked to me about it, so I was pleased.
I'm sorry, we run out of time. This lunch hour, so I have to cut this.
Great. Thanks for